And now I wish to using this class to give you a bit more about the torsion of non-circular cross-section, which means non-circular bar, and can be applied to a twist rectangular bars. Okay, so you might see that something interesting will be coming up. So the goal is I will give you a review of the old stuff and the circular torsion, the torsion of the circular bars, and then learn the new techniques. And basically here we won't go into detailed technical derivations, but if necessary, then I will provide you the formula from our textbook for taking care of the twisting of the rectangular shaft. Also, the textbook addresses a very, very powerful theory called the membrane analogy theory. And that one can help us to visualize, get a feeling, very good feeling about how the distribution of the stress, strain stress in the shaft. And that is a very fun topic. And so that is the objective in this lectures. Okay, so with this one, keep in mind the first one is I will quickly give you the review of the circular cross sections, the torsion of the circular cross sections, and that one. And let me quickly review those things here. So keep these slides, and so that is the old one here. So for what we have learned is that we're dealing with based upon the simplest the torsions on the circular uniform bar. That means the cross-section area is the same, the circular everywhere. And in our the old derivations, we make the assumption is this: by taking any cross-section across the bars, and the cross-section under torsion will be original before deformation is circular cross-section, and after deformation still be the circular cross-section. And that is the first assumption we made before we derive the equation for the fundamental mechanism material. The second assumption is this: originally, before the deformation, before twisting, diameter AB, and after the twisting, the AB will simply rotate about the center to the new positions. So that means the before deformation and the diameter will remain as a diameter after torsion. Basically, the two assumptions, if we really want to integrate together, basically that's saying is any cross-section remain as a rigid body rotation during twisting. Okay, so that is the base for our analysis. And the same assumptions applied to let me think about that one. Okay, no. The same assumption probably not apply to this one here. So with those things, then see if I have the formula. Okay, so here let me quickly give you the expressions of the formula we can use. How about you? So this has the radius C, and this one is on the torsion. So, for example, here let me give this one. So the application of the torsion is in that direction. So in this way, this will be in this direction. Okay, so there's a torque. So the both way, if you use your writing rules, this torsion has the same is this. You use the right hand rule and circulate your four fingers with the circulation of the torque. The thumb indicates is the sense or the orientation of this torque. In this way, this torsion applied is in this sense. Okay. So from here you can see basically on the two sides the torsion are in balance. This one is in static balance. So under these situations, we know that, okay, so let me see the side view. So let me mark, and this is the side view on the surface. So this is the a mark line on deformed surface of a shaft. And then once we apply the torsion, for example, the twisting by this, so that means here let me use this double arrow to indicate the torsion. So double arrow to indicate the torsion, that meaning the orientation just like this case. So this will be deformed, and the relative deformations will be something like this one. Okay, so the originally is a straight line mark. After deformation will remain as a straight line. And those straight line properties are based upon our assumption. The rigid body and any cross section will remain as rigid body rotations. So for example here, if here on this side, say it's plunked against the wall, so that would be make this model more perfect. Okay. So basically from here you can see every cross section remains as the rigid body rotation due to this torsion. And this side is constrained without any rotation. So that means the farther away from the constrained side is moved down. So from the side view, so this is side view and this is the other front. Say, let me call this the front view. So that means here we're looking in this direction. Into that direction, then the torsion is applied in this sense. Okay. So this is the mark we look through from this viewpoint. So after tweaking this is the center here, that portion is moved to P. So this angle is phi. Okay, and phi is called the angle of the twist. The angle of the twist is proportional to the torque, phi and equal to T L over GK, and L is the length of the shaft. The larger the length, then the larger the twist angle. So T is usually T is even, okay, or whatever. And G is the called rigidity. Modulus, and L is the length of this shaft, and J is we call the polar moment of inertia. Okay. And for the solids, if this radius is C, so for solid shaft, J equal to pi over 2 C to the 4th power, and for hollow, so this is C2 and this is C1. So for hollow shaft, J equal to pi over 2 C2 to the 4th minus C1 to the 4th. Okay. So that is for taking care of the deformations. And then for taking care of the stress.